Hi, and welcome to the Foundations course lesson 8, Thoroughly Designing a Study, Part A, Introduction. So, in this lesson we are going to look at study designs, and we'll start off with the very basics. The first step is to evaluate your research question. And from there we will delve into the different types of research, and we will take a look at hypothesis generation versus testing, designing the data collection, designing the data analysis, and how to avoid bias. So let's start with the GCR study design process. The first step when you want to do clinical research is to define your research question. The second step is to determine your research type and your study design. And study design can actually be subdivided into the design of the data collection and design of the data analysis. Once you've done that, you need to determine your required sample size, and then write your study documents, register your study, and build a database. Okay, I'm going to show you how to use the GCR Statistics Research tool. You can access the research tool part on the gcrstatistics.com website, either by using this menu on top of the page or this link over here under our services. And if you click on research tools, you can choose between the study design tool, the test wizard, which we already discussed in a previous lesson, and even a sample size calculator for some basic sample size calculations. But let's look at the study design tool. If you click on this button, it will bring you to the landing page of the study design tool, in which at the first step you will get some help with defining your research question by stating your domain, determinant, and outcome. And you can click on this button to get an overview of the most important reporting guidelines in the Equator network. And these are all epidemiology statements that are actually asked for by many clinical journals to make sure that your study methodology is up to par with the standards. And in the second step, you can choose your research type and get some specific advice on how to design your study according to these epidemiology statements, with etiological research, diagnostic research, prognostic research, intervention research, and reliability or agreement research. And if you click on the button, it will bring you to the landing page of the specific study domain, in this example, etiological research. And on top of the page, you will get a summary of the most important characteristics of that study design. And I will provide some important links to the epidemiology statements that are applicable to this study domain. And all of the landing pages of the study domains have this general structure where at first I will discuss why you would want to form a study like this, what the biggest challenges are in this study domain, how to get started, and how to design the data collection and data analysis. So basically this is a short summary of what we will discuss in this lesson on thoroughly designing a study. And you can do this for all of the study domains. And then you can go to a sample size calculator with this button, start the calculator here, and we'll bring you to our web-based sample size calculator where you can determine sample sizes for the comparison of proportions, the comparison of means, and for correlations and regressions. You get some additional help about all of these items under the help button. And then, of course, we will remind you that after going through all of these steps, you're not done yet, but you should still think of these items. But I think that's pretty self-explanatory. So this is the gist of how to use the GCR Statistics Research Design tool. Let's go back to our lesson. We will resume the lesson on thoroughly designing a study by looking at the research question, which is the first step in designing a study. So basically, the research question is the problem that you are trying to solve with your study. And the first part of the research question is the domain. And in the domain, you should define the study population, so to which type of patient or disease you want to generalize your study findings to, and the study setting. And that's often the place of care. So it could be the general population or a general practitioner's office, the emergency department, the intensive care unit, or a tertiary academic hospital. And oftentimes this setting is forgotten in the domain, but it's very important because the prevalence of disease, for example, differs a lot between study settings. The second part to think about also begins with a D, is the determinant, and that is the variable that is under study. And this could be many things, like a risk factor or a diagnostic test and its reference test, or a treatment and its comparator, or a prognostic marker, for example. And the third component of the research question is the outcome. So that's the primary study endpoint that you're interested in. And this could also be many things, among which a relative risk of disease, a measure of diagnostic accuracy, a therapeutic efficacy, or a toxicity measure of a treatment, a patient-reported outcome measure, cost effectiveness, a clinical prediction model, and many other things. Now, by combining these three things, we can define our research question. Let's look at some examples to understand this a little bit better. In etiology, a research question could be, does smoking increase the risk of lung cancer occurrence in the general population, where smoking is the determinant, risk of lung cancer occurrence is the outcome, and the general population is the domain. In diagnostic research, can CT pulmonary angiography accurately rule out pulmonary embolism in patients with an elevated Wells score at the ER, where CT pulmonary angiography is the determinant, rule out pulmonary embolism is the outcome, and patients with an elevated Wells score at the ER is the domain. In prognostic research, it could be, is HER2/neu receptor status an independent predictor of survival in patients with newly diagnosed breast cancer, where HER2/neu receptor status is the determinant, an independent predictor of survival is the outcome, and patients with newly diagnosed breast cancer is the domain. An intervention question could be, does intra-arterial thrombectomy improve functional outcome in patients with acute ischemic stroke compared to usual care alone, where intra-arterial thrombectomy is the determinant, functional outcome is the outcome, and patients with acute ischemic stroke is the domain. And of course, the usual care alone as a comparator is also part of the determinant. And it's good practice to include these comparisons in intervention research questions, but actually also in diagnostic research questions, you can include the reference standard that you use. And in reproducibility and agreement studies, it could be, what is the inter-rater reliability of radiologists reading pulmonary CTA in hospitalized patients suspected of acute pulmonary embolism, where the inter-rater reliability of radiologists is the outcome, reading pulmonary CTA is the determinant, and hospitalized patients suspected of acute pulmonary embolisms is the domain. Now, I believe it's really important to come up with a very specific research question, because it forces you to think about the essence of your study. What is the question that you want to find an answer to? And the problem oftentimes is when you look at the published literature is that authors do a good job on explaining the rationale for the study and how they performed the study in their introduction section. And oftentimes they also state a study goal, but that may include a lot of distracting factors like the complexity of the study design, the fact that the study population may be a little bit different from the intended domain, and many researchers also want to study multiple hypotheses in one study by including all kinds of secondary endpoints and post hoc analyses or subgroup analyses. And that all adds to some complexity of the research. But the most basic element that will help you to have clinical impact is coming up with a really specific research question. And it's actually a really good exercise to look at the published literature and come up with the exact research question for that study, and then compare it to how the authors describe their research goal, and see if they actually do pose the research question specifically in their manuscript. And now that we have stressed the importance of research questions, let's move on to the different research types in clinical research. There are basically 5 important types of clinical research: etiology, diagnostic, prognostic, intervention, and reproducibility and agreement. So what's the difference between these types of clinical research? Let's start with the causal research types. In causal research, we want to establish a clear cause and effect relationship. So that means that we need to take care of so-called confounding factors. And the only causal research types are etiological and intervention research. Whereas in prediction research, it is only important whether a set of variables can predict a certain outcome. It doesn't matter whether it's inside or outside the cause-effect relationship. And although confounding doesn't matter in prediction research, other factors can be influential. And we will discuss effect modification or interaction as one of the important factors later on. The 3 prediction research types are diagnostic, prognostic, and reproducibility research. So we have already made a distinction between causal and prediction research. Another distinction that is important is that of intervention versus observational research. In intervention research, we deliberately change the condition of patients by intervening, and mostly in a therapeutic way. In observational research, we don't do that. We only observe a group of patients and study their characteristics. Note, however, that a study on a therapeutic topic can still be observational research. For example, if we look at prognostic factors in patients that are all treated with a certain type of surgery, then we don't deliberately change the status of some of the patients and compare that with the others. But we study all of them, and although they were treated with surgery, that's not the topic of investigation in that study. And on the other hand, a study on a non-therapeutic topic can also be intervention research, where, for example, we look at the introduction of a diagnostic test in the clinical workup of patients suspected with a disease, and then compare that to a group of patients that do not get that diagnostic test in their workup. And another distinction in research types is that of time. So on one hand, we have cross-sectional study designs, and that's diagnostic research and reproducibility, where we want to know, for example, in diagnostic research, whether a test can predict if a patient is diseased or non-diseased at the time of the diagnostic test. So we're predicting something in a cross-sectional fashion, whereas in all the other study designs such as etiology and intervention and prognostic research, we do follow patients up to see whether they develop an outcome of interest or not. And you can basically see those research types as being longitudinal as opposed to cross-sectional. And now if we put all of this together, we can subdivide the study designs accordingly into observational research, with etiology being the causal research type, and diagnostic, reproducibility, and prognostic research being prediction research that is observational. And then the other type is intervention research, which obviously is intervention, but also causal. And only diagnostic and reproducibility research are cross-sectional, whereas all the other study designs have time as an element of the research. And now that you have determined your research question and research type, you can start designing your study. And the study design itself can be subdivided into two parts: the design of the data collection and the design of the data analysis. We will explore these parts in detail in the upcoming parts of this lesson, but I just want to tell you that these are already some of the most important facts to know about study design. One more thing to keep in mind, though, is that performing a study can be done for several reasons, and I think it's important to state the reason of performing your study very clearly. And you can subdivide your research into two broad categories. You can either perform a study for hypothesis generation, and that's usually true for early phase studies that are very innovative, have a descriptive analysis part, and can be directive for future research endeavors, whereas hypothesis testing studies are usually later phase studies that are translative and have a more analytical basis. And they can be potentially decisive for clinical research and have a direct impact on patient care. And we certainly need both types of research. In general, for both types of studies, you should write a study plan in advance. So that doesn't mean that you can just go off and test all kinds of things and then call your study a hypothesis generation study without a pre-prepared study plan. And if you have performed a hypothesis generation study, be transparent about the fact that your study is pretty descriptive, and don't try to sell it as a hypothesis testing study with all kinds of complicated analyses on small subsets of patients that don't contribute to the educational value of the hypothesis generation study. Just be proud of the innovative characteristic of your study and try to share your newly acquired knowledge in that research type with the community. And this will oftentimes get you much further than claiming all kinds of things that you cannot back up. That actually brings me to the analogy of not squeezing the lemon too hard, because I believe that you should refrain from some kind of mixed study in which you have performed an early phase small study claiming innovation using a heavily data dependent analytical approach and overstating your impact. Unfortunately, those types of studies are published on a daily basis. Of course, these are no laws, but I think that sticking to your specific research question and using data analyses to serve as a tool to answer that research question instead of serving as a purpose on their own will bring you much further in the long run and increase your chances of being able to impact clinical medicine instead of just scoring some publications and adding to the mass confusion of irreproducible research. All right, now let's look at the designing the data collection. So what we're going to talk about in this section is prospective versus retrospective studies, the four common study designs, among which are the cohort study, a cross-sectional study, case control study, and a randomized controlled trial, and different study designs per research type. What we're not going to talk about is the more meta type of research, including systematic reviews and meta-analyses, since this will be the topic of future courses. So, what is the goal of designing a study? We can subdivide it into two different goals. The first goal is to create the circumstances necessary to answer the specific research question in the best possible way. And for this, we need validity. That means that our study is not biased and we are actually measuring what we think that we are measuring. We need precision. This means that we can estimate our parameters with an acceptable level of uncertainty. And the study needs to be feasible. And the second goal is to create transparency about the study plan before starting the study, as a means to decrease the likelihood of some kind of manipulation by the researchers or sponsors. And in this sense, a good, transparent study plan can increase the confidence of other researchers evaluating your study and thereby increasing the likelihood of the acceptance of your study findings. And you should keep in mind that another independent researcher should be able to conduct the study in a similar way using your study plan. So that's the level of detail that is necessary in your study design. Now, we can distinguish prospective and retrospective studies. And this difference lies in the data collection and not the analysis. So in a prospective design, the study is planned ahead of time and new patients will be included from the start of the study. And this means that you can standardize all study procedures. The biggest advantage of using a prospective design is that it will provide the strongest available evidence compared to a retrospective design, since it tends to create more homogeneous study groups and it increases the ability to limit bias in the study and limit missing data. The downside, however, is that it is costly with regard to time and finances to run a prospective study. A retrospective study design is planned after the data are already collected using an already available data source like the electronic patient chart or some kind of registry. And in retrospective studies, the study procedures are generally not standardized. So the benefit here is that it is a feasible study design since it is oftentimes readily available and it's not costly in terms of finances and time. And it is generally useful for some kind of hypothesis generation and studying rare outcomes or diseases. However, it does provide the weakest available evidence since it tends to create more heterogeneous, very selective groups that may be prone to bias and missing data. Two additional points are that a randomized controlled trial is always prospective. However, almost all retrospective studies are observational. And by definition, a randomized controlled trial is causal and intervention research, and retrospective studies are observational but can be either causal or prediction research. All right, so now we will move on to the four common study designs: cohort study, cross-sectional study, case control study, and the randomized controlled trial. We are going to discuss these study designs in detail now. Let's start with the cohort study. A cohort study is a study in which a group of study subjects is followed over time to observe whether they developed an outcome of interest. And this can be done in a prospective way, where we start with collecting the baseline characteristics and then prospectively in time follow them up until they develop an outcome or they don't. Or we can do this retrospectively by collecting the data on the baseline characteristics, the follow-up, and the outcome simultaneously. And the biggest benefits of this study design are that multiple outcomes can be studied simultaneously. It is an ideal study design for determining natural courses of disease or disease incidence, and it often reflects clinical practice pretty well. Furthermore, multivariable modeling does allow for some degree of cause-effect estimation, but there are also disadvantages. Retrospective cohort studies especially are prone to bias, and prospective cohort studies are expensive and time costly. Furthermore, for inference of causality, it's not as suited as a randomized controlled trial, but on the other hand, a randomized controlled trial is not always ethical or feasible. In a cross-sectional study, a group of study subjects is simultaneously evaluated with a diagnostic test and a reference standard to determine whether at the time of the diagnostic test, patients have a certain outcome, which is usually a disease. And so you can see that both the determinant of the study and the outcome of the study are evaluated at the same time. And that's why we call it cross-sectional, because it's cross-sectional in time instead of longitudinal as in a cohort study. Some people actually see a cross-sectional study also as a type of cohort study, but I prefer to keep these two entities separated. However, I do want to note that sometimes the reference standard includes follow-up over time. And the reason for that is that it could be that the reference standard is imperfect. So there's no good way to determine at this time of the testing whether a patient has a disease or not. And sometimes the only way to find that out is to wait and see how, for example, symptoms develop over time, or whether patients respond to a therapy that would indicate that they have that specific disease. And so with this information in the follow-up over time, you can sometimes project back with more certainty whether a patient had a disease at the time of the diagnostic test. And the benefits of a cross-sectional study are that this is the go-to design for diagnostic studies, and it's a very efficient design. Furthermore, it's the best way to study disease prevalence, but there are also disadvantages. Only one outcome can be studied, and causal inference is not possible. Cross-sectional studies are always prediction research. All right, let's move on to the case control study. In a case control study, patients with a certain outcome of interest, called cases, are actually selected from a larger group, together with comparable patients who do not have the outcome of interest, and those patients are called the controls. And when we have selected the cases and the controls, we are going back in time to see whether there's a difference in baseline characteristics that might explain why some people develop the disease, whereas other people don't. Case control studies make sense for rare outcomes or first principle studies for new diagnostic tests or biomarkers that are expensive. And they only allow for the generation of relative measures of risk, and since the common study endpoint is disease or non-disease, oftentimes an odds ratio is calculated because researchers want to adjust for confounding variables in a logistic regression analysis. And a very important point is that the controls should be selected randomly. The benefits are that it's a very efficient and sometimes even the only feasible design in rare outcomes. And the disadvantages are that since the direction of analysis is reversed, because we're essentially looking at baseline characteristics as the study outcome, the strength of evidence is greatly reduced. Furthermore, case control studies are prone to bias. The last study design to be discussed is the randomized controlled trial, where patients are randomly allocated to one of multiple different treatment groups. Most oftenly, we have 2 parallel groups, and then they are followed over time to see whether they develop a certain outcome and whether there's a difference in the outcome developed between these 2 groups. The benefits of randomized controlled trials are that it's the best study design for causal inference in intervention studies, due to the fact that we can create equal treatment groups, due to the fact that we can create comparable groups with regard to their baseline characteristics, and thereby eliminate confounding factors. And multiple outcomes can be studied in a RCT. Furthermore, we can obtain both relative and absolute risk measures. The disadvantages are that this is by far the most expensive, labor and time costly study design, and it may not always be ethical or feasible. Another disadvantage of RCTs is that they often create highly selected groups of patients due to stringent exclusion criteria, and this may not reflect clinical practice best. There are certain essential elements to consider regarding the data collection. First, we need to look at the study design. So we can either use a prospective or retrospective cohort study, a case control study, a cross-sectional study, or an RCT. And we need to think about the patient accrual. So where do we get our patients for the study? What is the study setting? Are we looking at primary care, a secondary, or maybe even a tertiary hospital? What is the expected period of recruiting the patients, the time of potential exposure to determinants in the study, as well as the follow-up time, and the specific eligibility criteria in terms of in- and exclusion criteria, with their specific reasons. And then we need to think about the variables of interest that we also call the determinants. And for all study types, this means which patient characteristics are we interested in? What is the severity of the target disease or alternative diagnoses in diagnostic studies? And for etiology and prognostic studies, we need to think about the candidate risk factors or predictors and the outcomes with specific definitions and how we determine them. In diagnostic studies, we need to think about the index test that we use and the reference test or standard, and obviously the methods to assess these tests, the precise methodology for measurements, who will assess the tests with which level of experience, how do we define a positive or negative or maybe even indeterminate test outcome. And for intervention studies, we need to think about the type of randomization, the necessity of blinding, and the specific details with regard to the treatment and investigational procedures. And then lastly, for the outcomes of interest, we need to define a primary endpoint, which is also the target of the sample size, and we need to determine secondary outcomes of interest. And we need to be very specific about their definition and indicate whether these are single outcome endpoints or composite outcomes. And we need to make sure that we know how and by whom they are assessed. Voila, that's the basics of designing the data collection. Now let's move on to designing the data analysis. So, essential elements to consider regarding the data analysis are pre-planned analyses, sample size calculations, and post hoc or subgroup analyses. We also need to think about the tests used for categorical or numerical data, handling of dependent or clustered data, handling of missing data, so we could think about something like imputation, multiple testing correction methods, and the significance levels used for different types of tests, including whether we use one or two-tailed tests. Specifically for a model building, we need to state the purpose of the model, the type of regression model used, how we evaluate model assumptions, how we select candidate variables, how we transform or categorize data, how we update models, and how we assess calibration, discrimination, and internal validation. Specifically for intervention studies, we need to state whether we use the intention to treat or per protocol principle as the primary way of analysis. And for reproducibility studies, we need to specifically state the measures of agreement and reliability used. Let's look into bias, because this is a very important topic. And there are specific ways to avoid or at least lower your chances of bias in study that you can use to your own advantage. We already know that the goal of clinical research is to explain the relationship between determinants and a certain outcome in the population. However, we measure these parameters in a random sample, and there's always some random error in this estimation. And this is a natural periodic fluctuation that affects precision. It is equally likely to affect the determinant outcome relation positively or negatively, and it decreases with increased sample size. Furthermore, the amount of random error can be mathematically estimated and adjusted for. However, systematic error is different, and the sum of random error and systematic error is the total error in our estimation. And systematic error is also called bias, and this should be avoided as much as possible because it affects the study validity. It selectively affects the determinant outcome relationship in either a positive or negative direction, and it remains unchanged with increased sample size. Unfortunately, it may be impossible to adjust for some sources of bias after they have occurred. And due to bias, we may draw erroneous conclusions on the determinant outcome relation in the population through our parameter estimations in our random sample without even being aware of it. In essence, everything that could distort this determinant outcome relationship in the target population is a source of bias. But we can simplify it by subdividing sources of bias into 3 categories. The first category is selection bias, the second category is information bias, and the third category is confounding. And we will discuss these types of bias sources in detail now. In selection bias, the problem is that the study population is not a random selection from the target population. So the recruited individuals are not representative of the domain. And the underlying cause can be that you as a researcher may have unconsciously made a selection. The selection may be part of an existing database or infrastructure, or certain patients may have even selected themselves. And there are special types of selection bias. In confounding by indication, clinical indication for selecting a treatment also affects the outcome. In allocation bias, systematic differences in how patients are assigned to the treatment and comparison group in randomized controlled trials arise. In attrition bias, loss to follow-up is not at random, but related to clinical outcome, and thus differs between patient cohorts or treatment groups. And the remedy for selection bias is to construct a careful study plan. So think about potential sources of bias ahead of time. And choose a suitable source for participant recruiting that carries the lowest risk of selection bias. Train recruiters not to develop a preference for who can or can't participate in the study. And record patient characteristics of all patients screened for participation, including those that were excluded or declined, together with the reasons for exclusion, and those included in the study. This way you can at least get a good sense of the chance of selection bias being present in your study. Furthermore, you should also try to record reasons for dropout and loss to follow up, and this may require a very active role of the researcher because it can be hard to uncover the real reason for dropout in patients. But it is important because it gives you an idea of whether someone selectively dropped out, causing attrition bias, or just didn't feel like contributing to the study while this wasn't related to the study outcome. And it should be noted that randomization, if performed adequately, may resolve selection bias. Now, in information bias, the determinant-outcome relationship is influenced by selective or inconsistent data collection. And the underlying cause is that the data collection differs between patient groups due to influences by either the patient, the observer, or a measurement instrument. And there are special types such as observational bias, where the awareness of being observed changes a study participant's behavior. A recall bias, when one study group or subgroup has a differential recall of exposures or events prior to the onset of disease. And this is a common problem in observational studies using questionnaires as a measurement device. Misclassification bias, where a study participant is categorized into an incorrect category, and this affects the relationship between determinant and outcome under study. And observer bias, where the determinant or outcome assessor, and we call this person the observer, is influenced by knowledge of the patient allocation in a randomized controlled trial or patient characteristics. There are several ways to prevent information bias. For example, incomplete informing of the study goal. So sometimes the real purpose of the study shouldn't be disclosed to participants. However, ethical committees must agree to this, and this technique is more often used in psychological research than in clinical medicine research. Using objective proxy variables, so an example for this could be, instead of using the visual analog scale to measure pain scores, you could also look at the pain medication use. Training the data collectors to be objective in their data collection. And one of the strongest techniques is blinding. So if this is possible, at least the outcome assessor needs to be blinded to patient status. So for example, an observer evaluating a diagnostic test shouldn't be aware of the reference test results. And the same goes for treatment allocation in randomized controlled trial. And blinding prevents observer bias. In addition, the patient can also be blinded in intervention trials to prevent observational bias. And there are different degrees of blinding. So common nomenclature is that single blinded means that only the patient is blinded. Double blinded means that the patient and treating staff is blinded. And triple blinded means that the patient, treating staff, and the outcome assessor are blinded. Alright, in confounding, the problem is that a variable is associated with both the exposure or determinant and the outcome. In this situation, the association between determinant and outcome that is measured can actually, at least partially, be explained by another measured or unknown factor. And per definition, a confounder has to predate the determinant in time. So the confounder has to already be present before the determinant is measured, and otherwise it is just a mediator. And confounding is one of the biggest problems in observational research and should be addressed correctly. Important remedies for confounding are, of course, using a large randomized controlled trial. This is the best solution available, since it also controls for unknown and unmeasured confounders. But the downside is that it's not feasible or ethical for some research questions. And the other option is to use stratified analysis or multivariable regression models, since this allows for separate conclusions for the different subgroups, but it can only control for the known and measured confounders, and it requires enough patients with and without the confounding factor to be of value. Confounding and effect modification are two different entities. In confounding, we think we are measuring an association between a variable and the outcome, but what we're actually measuring is the association between the variable and a confounder, and then the subsequent association between the confounder and the outcome. So this is the direction of association that we're actually measuring. And in effect modification, the association between a variable and outcome is modified by another variable called the effect modifier. And it can be enhanced. In that situation, we refer to it as synergism, but it can also be reduced, which is called antagonism. So this is the difference between confounding and effect modification. And the important thing to note is, although confounding is not an issue in prediction research, such as diagnostic and prognostic studies, effect modification is important to take into account in these types of research. Whenever you want to evaluate the risk of bias in a study, it is a good start to ask yourself the following questions, which will sort of summarize what we have discussed before. Are the study subjects representative for the target population, since this tells us whether selection bias can be present? Are the subjects in the study arms comparable? If not, then there's a risk of confounding. Is the information collected in a comparable manner? If not, then information bias may be present. Are potential measurement errors described? Does the study design allow for potential sources of error? How good is the quality of the collected data? And are correction procedures used? And if yes, which ones? That's about it for the introductory part on Lesson 8, Thoroughly Designing a Study. Again, great job hanging in there. And in the subsequent parts of Lesson 8, we are going to explore the most important aspects of study design for each of the research types in detail.